Welcome to Pertech Learning and Development. This is a supplementary lecture on triangles in engineering. The day-to-day activities of engineering tradespeople involve calculations, and a lot of these calculations involve triangles. The examples and applications used in this lecture were referenced from the above textbooks: the Engineering Machine Shop Calculations and the Fitting and Machining Trade textbook. There are plenty of online resources and courses, free and paid for, that you can reference as a student to improve your mathematics skills. Persistence, repetition, and practice will be required to master the methods and formulas covered in this unit. Don't forget to check out Moodle for resources on this unit. Triangles. Triangles are everywhere, and they are very useful in science and engineering, as they have certain predictable behaviours that can be manipulated to solve engineering problems. Triangles are made up of 3 sides and 3 angles. Triangles are everywhere. Look around your room, or look up and around when you go for a walk. Most probably a triangle was involved in the construction or the calculation of everything you see, from buildings to calculation of electrical power to construction to the environment, cars, trucks, everything. As engineers, we use triangles to calculate shapes of the things that we're manufacturing. Think about taper turning, cutting angles, fabricating things. Triangles are even involved in the calculation of how much power our machine uses. Sine bars and sine vices are used on milling machines to set angles. And these angles are calculated using triangles. We use triangles for marking out and for determining positions or finding missing information. Trigonometry. Trigonometry is the name given to the branch of mathematics that studies relationships between side lengths and angles of triangles. Where it all began, Pythagoras. We've all heard the name Pythagoras. He was a Greek philosopher from around 580 BC who led a band of disciples who dedicated their lives to studying the natural world. Just a footnote, before the 1800s, a philosopher was a scientist, engineer, and artist, all at the same time. Isaac Newton also referred to himself as a natural philosopher. Pythagoras believed that everything in the world could be explained by numbers. He proved by experimentation and exhaustive repetition the predictable relationship between the angles and the lengths of triangles. 2,500 years later, the same knowledge is used to explore the solar system. There obviously was considerable knowledge of the characteristics of triangles, even 7,000 years ago with the pyramids. And right-angle triangles were referenced even back in the Babylonian times. But Pythagoras unified and standardized the theory of triangles. What makes up a triangle? Triangles have sides which have lengths. We can imagine them as lines. As we know, lines have a start point, an end point, a length, and a direction. 2 lines intersecting create an angle. Where these 2 lines intersect is called a vertex. Before we continue, something interesting's happened here. Have you noticed that the opposite angles are the same? Keep this phenomenon in the back of your mind, as it might come in handy later. When we talk about angles, where do these angles come from? What do they mean? Basically, philosophers took a circle and divided it up into 360 equal units, as ancient peoples thought a whole year was 360 days. As astronomy evolved and they discovered a year was 365 days long, but it was too late to change. I think dividing a circle by 100 or 1,000 would have made more sense. If we have three intersecting lines, we create a triangle. Another important phenomena to remember is that all three angles of any triangle always add up to 180 degrees, which is half the way around the circle, 360 degrees divided by 2. Here we can see that I've trimmed off the edges and now I have a completed triangle. There are 6 main types of triangle. Triangles can have various side length combinations and angle combinations. One angle less than 90 degrees, one angle greater than 90 degrees, and one angle at 90 degrees. The triangle that we created in our example is a scalene triangle. This is a triangle made up of 3 different lengths or side lengths. As we can see here, all 3 angles add up to 180 degrees. There are 2 main types of triangle. The right angle triangle, where one of the corners is 90 degrees, in other words, a quarter of the turn around the circle, and the non-right angle triangles, where none of the corners are 90 degrees. The formulas for using triangles can be divided into 2 categories: right angle triangles and non-right angle triangles. So we'll create a tree with 2 main branches. Let's populate our tree with the formulas that you would use for these specific situations. In this lecture, we will be concentrating on right angle triangles, as they represent about 90% of the triangles that you would use in your day-to-day workshop calculations. The formulas are divided into 2 categories. Category 1, if I have a triangle with only lengths or a few lengths, or category 2, I have triangles with some lengths and some angles. Just note that sometimes we'll need to use formulas from both categories to solve triangles. Pictured is a right angle triangle. As you can see, the protractor measures it at 90 degrees. A 90-degree corner will usually have a small square identifying the 90-degree corner. Which formula do I use to solve my triangle? When I say solve a triangle, I mean find the missing information or complete a triangle. For example, does my triangle have 2 of the 3 lengths and I need to find the third? I'll use Pythagoras Theorem. Or does my triangle have 1 length and 1 angle, or 2 lengths and I need to find an angle? Then I use trigonometry. Pythagoras Theorem. Firstly, let's look at the Pythagoras Theorem, where I can use a formula to find a missing length of a right angle triangle. Here we can see c squared equals a squared plus b squared. What does this mean? Let's have a closer look. Before we continue, you're going to need a scientific calculator, or you can use the scientific calculator function on your mobile device. If you don't have a scientific calculator or a mobile device, there are plenty of free websites and apps available online to do the same job. In mathematics, the Pythagorean theorem or Pythagoras theorem is a fundamental relationship amongst the 3 sides of a right angle triangle. In plain English, there's a predictable ratio between the hypotenuse, which is the longest length of the triangle, and the 2 other lengths or sides. In other words, if we have 2 sides of a right angle triangle, we can work out the third. Before we look at the formula, let's look at some terminology. The first term that we're going to learn is hypotenuse, and it's always denoted with a small c on a triangle. This is the longest length of a triangle, and it's always opposite our 90-degree corner. As we can see here, we have a little 90-degree square at the corner, and we can see the relationship of the hypotenuse to the 90-degree corner. Again, the hypotenuse is always the longest length of a triangle. We can see the labeling on the triangle. Usually small alphabetical letters are used for the sides or the lengths, and sometimes the sizes of the triangle can be on the triangle or they can be listed somewhere else on the document. The Pythagoras Theorem formula is c squared equals a squared plus b squared. All right, the small letters relate to the sides of the triangle. What does squared mean? C squared means c times c. A squared means a times a. B squared equals b times b. And remember, from our order of operations, being a squared, it has to be solved first. So we'd solve the squares and then we'd do the addition. So multiplication and division before addition, and obviously orders and square roots are done before multiplication, division, and addition and subtraction. So we can see our ordering of mathematical operations at the bottom of the screen. Here's an example on my scientific calculator of putting 40 squared straight in to give me 1,600. Now I could have done 40 times 40 and that would have given me the same answer. And on the other side here we can see the square root of 1,600, which is 40, which is the reciprocal of the square, or the opposite. Let's do an example. Let's solve for c. Remember, c is the longest length of our triangle, which is the hypotenuse. Let's populate our formula. So c squared equals a squared, which is 30 squared, plus 50 squared, which is b. Remember our order of operations, orders before division and multiplication, and all of those before addition and subtraction. So we have some squares, so the squares have to be solved first. So let's highlight in green what we have to do first. And 30 squared needs to be solved first, and 50 squared needs to be solved first. Now we can add the result, which is 900 plus 2,500. Take note of the order of operations. I need to make c the subject of the equation, so I need to get rid of the squared. I get rid of this by square rooting the other side. As you can see on my order of operations, the square root is the reciprocal of the squared, or the opposite. Now that I've made c the subject of the equation, I can complete my calculation. So I'll type in there's a square root of 3,400 in my calculator, and I'll get the length of c. And our length is 58.3 millimeters. We can see here that the hypotenuse, or the c, is the longest length. Let's do another one. Now let's find a. If we're looking for a, we'll have to make a the subject of the formula. It's important to take note of the order of operations. Let's do another one. Let's find b. This time we need to make b the subject of the formula. So now it's b squared equals c squared, which is the longest side minus a squared. Here we can see our B length is 40 millimeters. Here's a little formula sheet that you can use to help you solve Pythagoras Theorem. A, B and C are the sides we're looking for. We can populate our table and solve. Pause the video and take a screenshot of the slide, or you can download this template from pMoodle. The formula sheet is based on the ABC right angle triangle. And don't forget about your order of operations. Here's an example of using my template and my scientific calculator. Let's look at some of the general labeling of triangles. As we saw with Pythagoras Theorem, we label the sides with small letters. And of course, the hypotenuse is always the C. In the next section of the lecture, we'll be looking at trigonometry, which involves sides and angles. Angles are usually uppercase letters. In this example, an angle is described by a combination of capital letters, in this case, angle BCA. Here's another example. We have a 60-degree angle, which is directly referenced, or we can have angle specified as an alphabetical letter, in this case X equals 30. It is not uncommon to see letters of the Greek alphabet used to describe angles also. Now let's look at trigonometry using lengths and angles to find missing information. In this diagram we have two lengths or sides. With these two lengths we can calculate the missing angles. In this diagram we have an angle and one length. With that angle and length we can calculate the other two lengths. In total, you'll only have to know 4 formulas. We've already looked at the Pythagoras Theorem, that's the first formula. Now we have to have a look at the other 3, the trigonometric formulas: sine, tangent, and cosine. Here we can see sine equals opposite divided by hypotenuse or over hypotenuse. Tan or tangent equals opposite divided by adjacent or over the adjacent, and cosine equals adjacent divided by the hypotenuse or over the hypotenuse. We're already familiar with the term hypotenuse. Let's have a look at opposite and adjacent and what do they mean. Before we proceed to the next slide, it's important to remember that you will have to commit these formulas to memory. A simple way to remember the formulas is so to a ka or so to a ka. For example, so or SOH equals sine equals opposite over hypotenuse. Toa or TOA equals tangent equals opposite over adjacent. And ka, CAH, equals cosine equals adjacent over hypotenuse. So toa ka or so toa ka. If I haven't done trig for a while, I always write so toa ka at the top of my page to jog my memory for the formulas. Okay, opposite, adjacent, hypotenuse. What do they mean? Well, firstly, we know the hypotenuse is usually the longest length and it's directly opposite the right angle corner. The hypotenuse always stays the same, but the opposite and adjacent will vary depending on the information we're looking for. Always remember, the naming of the opposite and adjacent side depends on the angle we have or the angle we're trying to find. For example, we have the 30 degrees here, so the opposite and adjacent naming will be based from the 30 degrees. And on this other example here, we don't have an angle, we have the Greek letter, but that's still the reference angle, and that's what the other sides are based on. We can see here the opposite side is the length directly opposite to the angle we're working with. The adjacent side, adjacent means next to, is the length or the side next to or adjacent to the angle. An easy way to remember this is opposite means opposite to the angle, and adjacent means next to the angle. And another little tip, the adjacent side connects the angle to the 90-degree corner. Okay, your turn. Pause the video now and make a sketch and see if you can name the opposite and adjacent lengths or sides of these triangles. How did you go? As we can see, the opposite side is directly opposite the angle, and the adjacent side is next to the angle. And yes, that's the side that leads directly to the 90-degree corner. Let's have a look. I've got a right angle triangle, I've got one angle and one length, and I need to find length A. So I'm going to have to use trigonometry. Okay, I have an opposite side and an adjacent side and an angle. In this example, I'm going to use tan, which is opposite over adjacent. I can now go ahead and populate my formula. I need to make A the subject of my formula, otherwise I won't be able to work it out. If I multiply both sides of the equation by 100, the hundreds on the right-hand side will cancel out, thus leaving A by itself and making it the subject of the equation. I type in tan 30 degrees in my calculator, I will get 0.5773502692 times 100, and my answer will be 57.733 millimeters, and I round it off to 57.80 millimeters. So A equals 57.80 units, or millimeters in this case. Here you can see I typed in tan 30 in my calculator to get the answer. I could also put the full formula in my calculator. This might vary from brand on brand of calculator. Refer to the calculator's user manual for details and examples. In this example, we've got two lengths, but we need to find the angle. There's an opposite and adjacent side involved, so we're going to use tangent, which is opposite over adjacent. Let's populate our formula. So tan theta, which is the Greek letter used for the angle, equals 57.8 divided by 100. So therefore tan theta equals 0.578. To get the answer, I'm going to have to use the inverse function on my calculator. And my angle is 30 degrees. To find an angle, we need to use the shift or inverse key on your calculator. Refer to your calculator's instruction manual for details on this function. Pause the video now and practice inputting this value into your calculator or into your app before proceeding. My calculator is pretty smart. It can work out the order of operations without me telling it. Again, if you're not sure, do some test calculations and refer to your specific calculator's instruction manual. Just a reminder, on your calculator and on some trig examples, the -1 does not mean 1 over tan or sine or cos. It just means reciprocal or opposite function. Let's do another one. Let's find C. We have the hypotenuse, which is C, and we have the opposite side. So sine equals opposite over hypotenuse. So we're going to be using sine. Let's populate our equation. Sine 25 degrees equals opposite over hypotenuse, which is 100 over C. And C is the length we're looking for. To solve this equation, we need to make C the subject of the equation. Firstly, let's get C over the equal sign. So if we multiply both sides of the equal sign by C, the C's on the right hand side cancel out, and now we have C on the left hand side of the equal sign. I need to get sine on the right hand side of the equal sign, so I can leave C by itself. So I'll divide both sides of the equal sign by sine 25. The sine on the left hand side both cancel out, thus leaving C by itself and the subject of the equation. So now let's solve for C. C equals 100 divided by sine 25 degrees. C equals 236.62 millimeters. As you can see, my calculator is pretty smart and sorted the order of operations for me. Your turn. Pause the video now and find B. How did you go? Let's first find our formula. So we have an opposite and adjacent involved. So it's tangent. So tangent equals opposite over adjacent. So let's populate our formula. So tan 25 equals 100, which is opposite, over B, which is adjacent. To solve, we'll need to make B the subject of the equation. Firstly, I multiply both sides of the equal sign by B. The B's on the right hand side of the equal sign cancel out, and my B is on the left hand side of the equal sign. I need B on its own on the left hand side of the equal sign, so I divide both sides of the equal sign by tan 25. The tan 25 degrees on the left hand side both cancel out, leaving B on its own. Now B is the subject of my equation, and B equals 100 divided by tan 25 degrees. And B equals 214.45 units, in our case millimeters. We could have used cos because we'd worked out the hypotenuse in the previous step. Have another go. This time, pause the video and find angle theta. In this example, you had 3 sides. Therefore, we could have used sine, tangent, or cosine to find angle theta. In this example, I used cosine, which is adjacent over hypotenuse. So therefore, let's populate our formula. Cos theta, which is the angle we're looking for, equals 214, which is adjacent, over 236, which is the hypotenuse. Therefore, cos theta equals 0.907. Remember, we're looking for the angle, so it's inverse cos 0.907. Our answer is 24.90 degrees. I was looking for the angle, so it's shift cos, or cos to the -1. Sometimes we use trig and Pythagoras to find missing information or angles or lengths of a triangle. Let's check our previous trig example. with Pythagoras. C squared should equal the sum of a squared and b squared. So both sides of the equal sign should be even. And yes, if I follow my equation through, 236 equals 236. Obviously I rounded it off for the purpose of the slide. Let's look at some real life trigonometry problems that we'd need to solve in our day-to-day activities in a machine shop. Here is a sine bar. It's a common tool used to set angles on milling machines and drill presses. I need to mill a 30-degree slot on a workpiece. What size slip gauge do I need to put on the sine bar to give me 30 degrees? What information do I have? Well, I have an angle and a length, so it's going to be trigonometry. What sides do I have? Well, I have an hypotenuse, which is 100, which is the length, the C distance on the sine bar. I'm looking for G, and I have an angle. So opposite over hypotenuse is sine. Let's populate our formula. Sine 30 degrees equals G, which is the height I'm looking for, divided by 100. I need to make G the subject of the equation, so I'll multiply both sides of the equal sign by 100, and the hundredths on the G side cancel each other out, leaving G by itself. Perfect. Therefore, G equals sine 30 times 100. G equals 50. I'll need a 50mm gauge block on one end of my sine bar to give me 30-degree angle. I'm looking for a length, so it's sine 30 degrees times 100. In this example, I need to turn a taper between centers on the center lathe, so I'll need to offset the tailstock a certain distance to give me the correct taper. This doesn't require trig or Pythagoras, because I just take the biggest diameter of the taper, subtract the smaller diameter of the taper, and divide by 2, and that'll give me the offset distance for the tailstock. So it's 40 diameter minus 20 diameter divided by 2. The offset distance is 10 millimeters. What if I need to know the angle of the taper? What if I'm using a taper turning attachment and not turning between centers? Now I'm going to need an angle. Well, we've got a length and an offset distance. We've created a triangle. So now we have an opposite and adjacent side to the angle theta. So tangent equals opposite over adjacent, which is 10 over 80. So tan theta equals 0.125. We're looking for the angle, so it's inverse tan 0.125. Our answer is 7.12 degrees. Just a reminder, it was shift tan on my calculator because we are looking for the angle. Be aware that angles on mechanical drawings, especially turned components, are given in an included angle. That means if we were offsetting the tailstock or using a taper turning attachment, we would have to halve the included angle. In our case, we would set the taper turning attachment to 7.12 degrees to get a 14.24 degree included angle taper. Let's look at a real life calculation job. Mechanics sent me a hand sketch of a cylinder spacer. It's given me a diameter and a width of a slot. That's all the information he's given me. So I need to machine this up, but I need to get a bit more information. First thing I need to do is work out what the X dimension is. Do we use Pythagoras or do we use trigonometry? Pause the video now and have a go. I was able to form a right angle triangle using the radius of the diameter and half the width of the V groove. I have two sides. I'm looking for a third side, so I'm going to use Pythagoras Theorem. I'm looking for A, so I'm going to make A the subject of the equation. Observing the order of operations, I've worked out that A equals 15 millimeters. So the radius is 17 millimeters, which is half the diameter, plus 15 millimeters, the length I've calculated. My X distance is 32 millimeters. I will also have to calculate the depth of that V groove. I've rung the mechanic and he's told me it's about 90 degrees. Pause the video now and see if you can work out how we get the Y dimension. Let's have a look. I've made a triangle. I've got 8 millimeters. I'm looking for Y, and half of 90 degrees is 45. So I've created a triangle and I'm looking for the adjacent side and I have an opposite side. So tan equals opposite over adjacent. So tan 45 degrees equals opposite over adjacent, which is 8 over Y. Okay, to solve we need to make Y the subject of the equation. Multiply both sides of the equal sign by Y. The Y's on the right hand side cancel out and we end up with a Y on the left hand side of the equal sign. I need to get Y on its own, so I need to get tan 45 on the other side of the equal sign. So I divide both sides of the equal sign by tan 45, and the tan 45s on the left hand side of the equal sign cancel each other out. So I'm left with Y equals 8 divided by tan 45. And Y just happens to be 8 millimeters also. Just a quick note on special right angle triangles. We can see here on this isosceles triangle that both A lengths are the same. We can find the C length by multiplying the A length by the square root of 2. Going back to our previous example, we would have noticed that both angles were 45 degrees. That would have meant that the Y dimension would have automatically been 8 millimeters. So we would have been able to calculate that Y value without any formulas if we were familiar with special right angle triangles. Don't believe me? Let's check the isosceles special triangle, which has 45 degrees on both ends. Remember, all the angles have to add up to 180 degrees. We can see here that the hypotenuse is 8 millimeters times the square root of 2, which gives us 11.31 millimeters. Let's check that using, for example, sine. So C equals 8 divided by sine 45. Lo and behold, 11.31 millimeters. It works. Another special triangle is the 30, 60, 90 triangle. Again, this can be used to quickly determine lengths and angles. We can see the relationship of the sides with each other, but remember this only works with a 30, 60, 90 degree triangle. In this example, we have side A, which is 30 millimeters. The hypotenuse is 2 times A. The remaining side can be calculated by multiplying 30 by the square root of 3. Just a reminder that you could have solved the same triangle using tangent or cosine. Just a quick note on degree units. Degrees can be specified as a decimal or in degrees, minutes and seconds. It's recommended that you convert any degrees, minutes and seconds angles into decimal degrees. This is a simple formula. The degrees stay the same. We divide the minutes by 60 and the seconds by 3,600 and we add them up. So 60 degrees, 33 minutes and 18 seconds equals 60.555 degrees decimal. Your turn. Pause the video now and convert 30 degrees, 15 minutes and 25 seconds into decimal degrees. Let's have a look at this one. 30 degrees stays the same. Minutes, 15 minutes divided by 60 equals 0.25. And 25 seconds divided by 3,600 equals 0.0069444444. Add those up. That equals 30.25694. We round it off. It equals 30.257 degrees. My calculator converts them over quite easily. There's plenty of apps and websites you can visit that will also convert back and forth from the two systems. Here are a couple of examples that we did during the lecture using some free apps that I found on the internet. Don't be afraid to use all the tools and apps available to you to make your job easy and to get things right the first time. There are also great resources online like the Khan Academy, Trigonometry, and of course thousands and thousands of videos on YouTube.